Greetings. So now we will learn about the so-called scheduling problems, in which problem we have M machines. It's at least two for practical reasons. So we have M at least two machines, and we get as request sequences jobs, a sequence of jobs, and each job will have some processing cost. So in the base version of the problem, which we will modify later, but in the very base version we have a request is denoted by P because it's the whole sequence is just a series of some P1, P2, P3 and so on, Pn, with each Pi being some cost, which is just say some non-negative real number, so it's not an integer by definition. And an action, basically the underlying thing is that we have to decide when a job arrives on which machine should process the input. So an action just assigns a machine to each job. An action is, say, tau I, which is either 1 or 2, blah blah blah, or M. Okay. And the load of machine J, usually I will index the jobs by I's and the machines by J's. So the load of the machine J is, say, load J, which is just the sum of the processing times of those jobs which were assigned to this specific machine, and the so-called make span is the maximum load. Now this is the quantity which we want to minimize, and the make span, so it's make span is just the maximum load. And this is the thing which we want to minimize. Again, we want to minimize some maximum, right? Now let's see an example and how it's usually depicted. So for example, if M equals, say, 3, and the input, say, sigma, is just 1, 2, 3, 4, 5, 6, 7, 8, 9, for example, this means that the time needed to process the first job is 1. The time needed to process the second is 2 units, and so on and so on. And then a possible output sequence, possible response sequence could be, say, 1, 2, 3, 3, 2. So each job will be scheduled to one of those machines, 1, 1, 2, and 3. Okay. Usually we don't use this algebraic machinery, but we just depict them by pictures. So for example, if this guy is the first machine, so it's the ID of the machine is 1, 2, and 3, then this guy here says that a job of cost 1 will be processed on the first machine. So I will just put this here, a rectangle having a width of 1. here this guy says that a job with cost 2 will be assigned to the second machine. So I will just put here a rectangle with width 2. Here I will just draw a rectangle of width 3 on to the third, and this says that a job of cost 4 is to be put also on the third machine. Now at this point it doesn't make sense, and at this point the load here is only 1, the load here is 2, and the load here is 7, so it's just the total cost of the jobs which were assigned to the particular machine, and at this point the make span is this quantity here, the maximum load. Now after this, okay, so let's just continue. The job of cost 5 should be put to the second machine. Here it says that the job of cost 6 should be put onto the first machine, and at this point this wall scheduling makes sense. Suddenly it makes sense because, well, it's easy to check that 7 is the optimum at this point, but then we will have 7 to be put on the first machine, 8 to be put on the second machine, and 9 to be put on the third machine. So at the end, if we have this tau, then the loads are 14, 15 and 16, and the make span is 16 in this case. Now in general we won't be able to compute the optimal solutions for a specific input, so because it's exponential to compute that if you have at least 3 machines. So basically what you can do is lower bounds for the optimum. Remember, if we want to compute competitive ratios, then it's fine if we have lower bounds for the optimum and upper bounds for the solution. Lower bounds for the optimum L star, usually L star denotes the optimum, and L denotes so L star in the scheduling context, L star will denote the optimum value. On the value, so of course it's not an actual scheduling, it's not an actual output sequence, but just the cost, the make span of that output sequence. So first of all, when I said that this is easy to see to be optimal, well, it's because if I just put those things together, then the whole area of these rectangles I just drawn is just sum of pi, right? So it's a sum of pi. And if the width of this area is, say, L star for given an optimal schedule, and the height of this rectangle is m, then we get that the sum of the pi, so the total area of the small rectangles, is at most as large as L star times m. Because in general, well, if this would be an optimal solution, then, well, this would be the L star times m is the area of the large rectangle into which we packed all these smaller rectangles having a total area of sum of pi. Now this means that by rearranging we get that L star is at least as large as the sum of the pi's divided by m. Yeah, so that's one bound we could use. Another bound comes from the fact that the largest job also has to be scheduled to one single machine. So in this example, if I know that there is a job of cost 9, then I can do better than 9, because this job should be scheduled onto one of those machines, so the load of that machine will be at least 9 in that case. In general, L star, the optimum solution, is at least as large as the maximum of the PIs. So that's the second so-called general bound for this problem. And we will use these two bounds, these two lower bounds, frequently when we just compute competitive ratios of algorithms. Now, for this particular input, we get that L star is at least the sum of the numbers from 1 to 9, which is 45, divided by m, which was 3. So this bound says that L star is at least, the optimal solution is at least, has at least the cost of 15, and this guy here says that the optimal solution is at least 9. Now, if we just put these two together, we get that this is the better bound. So for this particular input, we get that the optimum is at least 15, and we already have a solution of 16, so it will be, since we are dealing with integers here, it will be either 15 or 16, and we can make it to be 15, so 15 is also achievable. So for example, if I want to make 15, then I have to schedule it like 6 plus 9, for example. That's 15. That's great. And then I have the 7 plus 8. And that's also great, because it means that the others, so it's 1, 2, 3, 4, and 5 are just totaling to 15 again, which means that the load of each machine will be 15, so 15 is the optimum solution for this case. Now, for the scheduling problem, we will study the simplest algorithm, a greedy algorithm, which comes into mind, so the so-called list algorithm. It says that let's put PI onto the machine, which is the least loaded one. The least loaded machine. Yeah, so if there are options in the case of ties, we should pick the the one with the smallest index. It doesn't really matter. With the smallest index. Now the list algorithm runs as follows on this input. So for example, if we have this 1 till 8 sigma just as before, and we still have 3 machines, then the algorithm will first, this is the first machine, this is the second, this is the third one, so 1 will be put here because each machine has a load of 0, and amongst the 3 machines, 1 is the one with the least index. Now then the 2, okay, so there are 2 machines. I'll just keep track of the load here. So here we have a load of 1, a load of 0, and a load of 0. And when the next query arrives, then say this guy is has the least index amongst of those having the least load, so it will have a load of 2 from now on. Now this is the unique minimum, so I will just put the 3 here. Okay, 4 comes to the first machine and the total load will be 5, because at this point the load of the first machine is the minimum. And now at this point, say comes the 5. That's great. Okay, and now comes the 8, and of course, and now the third machine has the least load, 6, sorry, yeah, okay, so it's 6, and the load will be 9, and then we will have the 7 to be put here, the 8 to be put there, and the 9 to be put there. You can verify that this guy here is still smaller than this guy. And right now the loads will be say 12, say 15 and 18, which means that for this particular input the list algorithm produces a solution of cost 18. Okay, now we can analyze the list algorithm. So the competitiveness of a list. So the list algorithm, there is a theorem, proposition, whatever you want to call. So it's exactly 2 minus 1 over m competitive. Okay, what does it say? So the exactly 2 minus 1 over m competitive is it means that it's we will give a bad input with ratio 2 minus 1 over m. Okay, and this will mean that this is either 2 minus 1 over m competitive or even worse. So this will give us the lower bound for the competitive ratio of list. And then we will prove that L, the cost of the output produced by the list algorithm, so it's L, is at most 2 minus 1 over m times L star for every input. And this is the proof of the upper bound. And since these two fractions coincide, lower and upper bound, this means that it's exactly 2 minus 1 over m competitive. Now let's just start with the easier thing, the lower bound by bad input. So it's lower bound for bad input. So what happens if, say, I just say m times m minus 1 jobs arrive of a cost of 1 each, and then a job of cost m. Then what happens? So first, the list algorithm will optimize as follows. So a large batch of unit cost jobs arrive, which means that I think I just stick to algorithm runtimes 1 and 1 and 1 and 1 and 1. Okay, so in this particular example I missed 5, but okay, so then it will load the machine here and there and here and there and here and so on. Okay, so if m is 5, then it then there will be 4 columns, but m can be arbitrary. But in general, this is how it looks like. Basically, I will just distribute it evenly, and since I have m times m minus 1 such jobs, it means that the width of this rectangle will be m minus 1. And then comes a job of cost m. The algorithm will put this onto the first machine actually, and if the first machine is the topmost one, then I should draw it like this. It might happen that in the lecture notes it's the other way around, and the bottom machine is the one with index 1, but it's not an important fact. So then we will have an additional m, and here L is 2m minus 1. While an optimal solution would just put this m here, like the first machine, say, and put the other jobs, 3 other machines, like this. Because in that case there are, so if this is one machine and these are m minus 1 machines and this wall width is m, then we have exactly m times m minus 1 jobs there. And the job of m is here, so L star is exactly m, because this wall rectangle is covered, so both general bounds give a lower bound for m. Now this means that I have to divide 2 times minus m by m, and then so the cost of the algorithm divided by the optimum is 2m minus 1 over m, which is exactly 2 minus 1 over m. Yeah, great. So we just proved by a bad input for this algorithm that it can't be better than 2 minus m competitive. Now let's try to prove the upper bound. So for the upper bound we have to prove that if let's start by scheduling produced by list, by schedule produced. By the list algorithm. So it can be just something like, okay, so there is a rectangle, there is another rectangle, and so on. There might be more of them, whatever. So in general we have some sort of arrangements like this. Okay. Now we know that this guy here is the make span, and this is what we call L. There is a machine on which there is a maximum load. So this guy here is the, say, the Lth machine. Not the machine, let it be the Lth job. So it's L job, the last job of a machine having a load L. Having a load of L larger. So what I do is just pick the most loaded machine and let PL be the last job of this machine, so this guy here. Okay, and just consider this part of the input. So here, at the time point when I just scheduled PL onto this machine, the second machine in this example, then all the other machines had the same load at least, because otherwise I would have put this job onto some other machine. So this means that at this point, so when we schedule this job, and all the other machines have a load of at least L minus PL. So each of the machines have a load at least L minus PL, because this was the minimum of the loads at that time, which means that all the other machines are loaded to at least. Now this means that if I just sum the costs of the jobs which arrived before PL, those will cover this whole rectangle, right? So basically I say that the sum of the jobs that arrived before the 11th job is at least M, the number of machines, times L minus PL. Okay, now I can make some sort of rearrangement. So first I'm just pushing this guy here, because for me at least an equal is more parsable, it's easier to parse. Okay, so I'm starting with this inequality, and then I just divide by M and add PL. This means that L is at most the sum of the jobs arriving before L divided by M, so that was the division, plus PL. Okay, now this is further equal. Okay, so this is J smaller than L, so I will just put 1 PL there, but this is divided by M, so it's equals J at most L PL P, oops, that's PJ, guys, that's PJ. That's PJ, okay, PJ divided by M plus, okay, so it's M minus 1 over M times PL. Now what's this? So it's at most, this is just a sum of the jobs, the cost of the jobs of till the 11th one, but which is just, since each job has a non-negative cost, if I sum the cost of all the jobs, then it's fine, divided by M, so it will be larger, plus M minus 1 over MPL. Okay, now we had two general bounds. One was this whole guy is a lower bound for L star, right? This was the first general bound. And second, this guy here is also smaller than L star, because in every schedule we have to schedule the nth job to somewhere, so the optimum cannot be smaller than PL. So this means that this is just L star plus m minus 1 over m times L star, which is exactly L star times 2 minus 1 over m. Right, because this is 1 L star, this is 1 again, and this is minus 1 over m. Which means that L divided by L star, so since L is at most this guy here, if I just divide the whole stuff by L star, it will be smaller than or equal to 2 minus 1 over m. And this proves the upper bound. So right now we got that the list algorithm, which is an algorithm for the scheduling problem, has a completive ratio of exactly 2 minus 1 over m. And in the next video we will see a lower bound for the best possible randomized algorithm by an application of the Yellow algorithm, which will put into perspective that whether it's 2 minus 1 over m is good or bad. Till then, bye bye.